Okay, good afternoon, students. Sorry for the late class. Okay, in the last class we discussed about the standard electrode potential variation for M plus 2 bar M. Today we are going to study same standard electrode potential for M plus 3 bar M plus 2 ions. That means in the bivalent ion, the one electron again removes, that is the ionization energy 3. For that ionization energy 3, we have to check the electrode potential. As I told you students, the ionization energy for scandium plus 3 is less. Okay, and Mn plus 3 is high and Zn plus 3 is very high. So this is the three comparisons are enough to say the standard electrode potential of these may vary in this form. So if you draw the graph, it will follow the trend in the increasing order. So as this is scandium, this is manganese, and this one is zinc. Okay, so it's keep on increases. So that's why the standard electrode potential of this plus 3 ion what? Plus 2. I already explained in the ionization energy, that is plus 2 second ionization energy and third ionization energy. So I won't take much time here. The next one which comes to is the stability in trends in stability of iron oxidation state. Iron oxidation state. Okay, students, to study the stability, we are going to consider halides as well as oxides. So by considering the metal halides and metal oxides, we are going to study the stability of the higher oxidation states. So in that, I told you the higher oxidation state is from plus 6 plus 7 for the manganese, plus 6 plus 5 plus 4 plus 3 and plus 2. Lower oxidation state is plus 2 and higher oxidation state is plus 7. So in that, scandium is there, scandium is stable in plus 3 oxidation state, but no one halides is formed by the scandium ion because it easily loses electrons means. So it attains noble gas configuration, it is quite unstable to satisfy the oxidation state. So the halides of scandium is unknown, okay, because they are unstable. But for titanium, in plus 4 oxidation state, this is titanium X4, plus 4 means polar electron less. So next, titanium X3 in 3 oxidation state free and titanium X triple dash 2. So what is this X, X dash, X double dash and X triple dash? I will say next, okay? So what are those represents? Otherwise I will write here students. X means chlorine, chlorine, bromine, iodine, all. X dash means, okay, chlorine, chlorine, bromine, but not iodine. Okay. X double dash means only chlorine and chlorine. X triple dash means only chlorine and iodine. Okay, so this represents this one. Okay, this means all the halides shows are stable in this oxidation state. Here also in plus 3 oxidation state, all the halides are stable. But in this lower oxidation state, only X triple dash means chlorine and iodine are known, and remaining these two are the chlorine and bromine are unknown. Similarly, for this vanadium, we have to find. Okay, next Vx4, okay, that is actually X dash 4, Vx3, Vx2. Okay, this is for vanadium. Titanium, vanadium done. Next one is chromium. In CrF6, Next, CrF5, CrX4, CrX3, CrX2. All the halides are possible in +4, +3 and +2 oxidation state, but only fluorine stabilizes the higher oxidation state, that is +5 and +6. If we take Mn means Mn stabilizes MnF4. The higher oxidation state of that is this much. And MnF3, MnX2. Okay. So this is what? The stability of manganese. And next one is iron. Iron is stable at only these states. Fex3 and Fex2. And last one is cobalt. Cobalt is also from HCF3 and COF3 and COF2. Okay? X. All the halides are known. After this, only chemical these two is possible. CuX and CuX. What is it? Xl primary means X dash is done. And CuX. Okay, so the last one is students. Next, zinc is there. Zinc is only, you may not see here. Zinc is 11x2. Zinc is also stable at all the oxidation states. So listen, here you assume in all the higher oxidation state, fluorine is there. Okay, all the higher oxidation state, what? Fluorine is there. So in all the halogens, the reactivity order, that is fluorine stabilizes the higher oxidation state than chlorine, bromine than iodine. So fluorine has the capacity to stabilize higher oxidation state. What is the reason for that? Because it has high lattice energy. Okay, because it has high lattice energy and high bond dissociation energy. So because of these two reasons, this fluorine stabilizes the higher oxidation states. So I listen, here X4 means it's 10 from fluorine, chlorine, bromine, iodine. In the order, fluorine stabilizes the higher oxidation very much compared to the other halides. So here also, here titanium X triple dash is there. X triple dash means chlorine and iodine are possible. Remaining are not possible. Why? Because this fluorine has a smaller size. It very, I told you this is a high lattice energy means it is the energy required or energy released when an isolated gaseous ion formed into what? A solid. Convert into a solid. That is solidifies into its 1 mole of a substance. Then it is called as what? Lattice energy. Because of high lattice energy, this fluorine stabilizes the higher oxidation state, you may say here. But what happens in manganese means? So manganese, the higher oxidation stabilized by this only halide is only +4. But if it is with oxygen, if this is present with oxygen, so then what happens? It stabilizes higher oxidation. If oxygen and halogen both are present, then only this stabilizes the higher oxidation state. Means in manganese compounds, alone halide, especially fluoride, never satisfies higher oxidation state. If it is along with oxygen atom or oxonium ions, then only they satisfies higher oxidation states. Okay, so this is all about the stability of higher oxidation state in halides. Okay, this is the reaction of the table. Next, you compare to oxygen, that is oxides. One side write oxides, then I will say What is the difference between stability of halides and oxygen or oxides? Okay. Compared to halides, oxides are highly stable. Okay, student. So here what happens? In oxides, all the oxidation states are there. That is +2, +3, +4, +5, +6 and +7. So here what happens? All the elements shows oxides or forms oxides in their respective oxidation state. For example, scandium, right here scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Okay. So students, as I told, this scandium shows +3 oxidation state means it has the formula SC2O3. Why this comes to us? So listen, scandium is +3 oxidation state, oxygen is -2. This is 3, this is 2. If we cross multiply, we get SC2O3. Same way we are doing for all the metals. Okay. So titanium exhibits T type of valency, that is +2, TiO, +3, TiO3, and +4 is TiO2. Correct? So next, vanadium. This vanadium shows +2, that is VO, next V2O3, next VO2, next V2O5. Correct? Again, for chromium, CrO, Cr2O3, CrO2 in +5, that is Cr2O5 and CrO3 in a +6 oxidation state. Next, for manganese, MnO in +2, Mn2O3, MnO2, Mn2O5, MnO3 and Mn2O7. Okay. Next is iron. Iron has the only +2 and +3 oxidation state and also +4. So here in +2 that is FeO, in +3 that is Fe2O3. But only these two are known. Another one is there, that is Fe3O4. That is also quite stable. Okay. So next, cobalt. Cobalt is CO2. CO2 O3. It is also stable in +3 oxidation state and also +1 oxidation state. So if we consider nickel, nickel is stable at +1 oxidation state. Copper is at zinc is also at stable at +1 oxidation state. So as I told you students, this is stable at +2 as well as +1. So this is the stability of what? Oxides. So here scandium is +3, +2, +3, +4, 2, 3, 4, 5, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, 7. So up to middle of the element, all the oxidation states after the block element shows their respective oxides. So okay, here chromium has 5 oxidation states from +1 to +2 to +5. So +6 means it shows 5 different oxides. Here also it shows 2, 4, 6 different oxides. So behind that manganese, what happens means they are stable at their respective oxidation states. Okay, so behind that iron or manganese, no one element has the oxidation state in the higher oxidation level. And means no one element has their respective oxides in the higher oxidation states. So their oxidation state of oxygen is stabilized, metals are stabilized by oxygen up to manganese, middle of the D block element would be. Okay. So here what happens, students? So listen, as I told you, this is the lower oxidation state, correct? And these are all higher oxidation state. Okay. So here what happens? The points you have to remember is oxides formed by lower oxidation state. Oxides formed by lower oxidation state are basic in nature. Okay. Next, oxides formed by higher oxidation state. Higher oxidation state. Then they are acidic. Okay, this is basic, this is acidic, very important. And last one, the oxides formed in between lower and higher oxidation state. So those are amphoteric in nature. Okay, those are amphoteric in nature. So students, these 3 points are very important for NEET oriented class. Why? Because they will ask different oxides of the D block elements. In that they will give these sentences, whether they are basic in nature, whether they are acidic in nature or amphoteric in nature. So you have to answer. So which you have to check the oxidation state of the respective metal, and if the metal is the oxidation state, whether it is a lower or higher, in between the lower and higher, then you came to know whether it is basic, acidic or amphoteric. So for example, I will take this chromium means this CrO is basic in nature, this CrO3 is acidic in nature. In between these 3 oxides are there, so those are amphoteric in nature. So that's what I wrote there. This is very important thing, students. Okay, so this is all about oxides. Okay, the oxides in after D block elements have, so on the oxidation state of metal shows their oxides up to the middle of the D block element, that is up to manganese, and behind that manganese only +2 and +3 states are oxidation state stabilizes the oxides. Okay, our oxygen stabilizes only +2 and +3 states behind this manganese before it stabilizes all the oxidation states of the metals. What is the reason? As I told you before, listen, manganese with halogen shows MnFO4. If manganese is with oxygen and fluorine means it shows MnO4 or MnO2F3. MnOF4 or MnO2F3. So here the oxidation state is +4, here the oxidation state of Mn is +6, here the oxidation state is +7. Okay, so students, here what we came to know, this fluorine alone never satisfies this higher oxidation state. When it is with oxygen, it satisfies the higher oxidation state like +6 and +7. What is the reason? Okay, or you can also say the halides of manganese in their higher oxidation state is less stable, but the oxides of manganese in their higher oxidation state are highly stable. Why? Okay, fluoride halides are less stable, oxides are highly stable. Why? Because students, So oxygen has the capacity to form multiple bond with the metals. So because of the formation of the multiple bond capacity, it can stabilizes the higher oxidation state of the metals. Only this is the reason they will ask for 2 marks in the examination regarding stability of the oxides. Then has these points are the as this thing. Why? Halides, manganese halides are less stable compared to manganese oxides. Okay. Or they may ask why oxygen stabilizes higher oxidation state of metals than fluorine. Okay. So this is all about the oxides. So another one thing is there. One example is there that Mn2 Mn2O7. What is the structure of Mn2O7? Means I'll write here, I'll rub this just. Here two Mn atoms are there richly bonded with this oxygen and remaining forms multiple bonds in a tetrahedral form. Okay, this is tetrahedral structure. And including this 1, 2, 3, 4, 5, 6, 7 bonds are there. Here also 1, 2, 3, 4, 5, 6, 7 bonds are there. Okay, so this is the structure of Mn2O7. So this is the reason here this forms what? Multiple bond, that is double bond. The capacity of formation of multiple bond with the metal atoms of oxygen results in the higher stability of oxygen in the higher oxidation state. Okay, so this is all about the oxides or the stability of oxides in its higher oxidation state. The question they will ask students, I'll write the questions here. Then you came to know. So questions asked in this is, why oxygen stabilizes the higher oxidation states of metal than fluorine. So this is the first question. Why oxygen stabilizes the higher oxidation state of metals than fluorine? Are the mass what is the reason for stability of metal fluorides than other halides? So the mass question, why the fluorides, metal fluorides are very stable compared to other metal halides? Because the reason is fluorine has high lattice energy and less bond dissociation energy. Okay, and a smaller size. Okay. Next, Dema has question by giving oxides, respective oxides. I will take Mn1, Mn3O, Mn2O5. What is the nature of the given oxides? What is the nature of the given oxides? Is the questions they will ask based on this stability of oxides and halides in the D block elements. Okay. So next one is chemical reactivity. So listen students, these are all D block elements and the metals. You know the metals are highly reactive. Okay, this reactivity depends upon the electrode value. The standard hydrogen electrode or standard electrode potential value gives what? The reactivity of the metal. Again, you know by Gibbs free energy, as I explained in the before chapter, that is a Lingard diagram, which one has the less delta G energy. As I told you, these are oxides. Okay, oxides are there, sulfides are there, haldes are there. So as they are oxides, sulfides, and haldes, they have the respective delta G value. If the delta G value is negative, then the reaction is feasible. Means if any two reactions are there, for example, chromium is there, manganese is there. Oxides of manganese has less delta G value. Okay, this is more delta G value, that is negative value. Which one is having high delta G value, that reduces this metal. Okay, so that is the way, that is the chemical reactivity, being these elements as a having highly electronegative, sorry, not electronegative, highly reactive. And again, I told in the standard electrode potential, what I wrote here, copper only have the positive graph or a standard electrode potential of a positive value. So that's why reason, that's why students, what happen, all the D block element metals reduces hydrogen. Okay, all the D block elements reduces for hydrogen. That means 2Cr plus 2 is there, plus 2H plus is there, gives us to what? 2Cr plus 3 plus H2. Okay, so this is what? Gain of electron, that is reduction. If reduction occurs, means this is the reducing agent. Okay, so all the metals reduces this hydrogen. Why? Because they have the negative electrode potential value. If the negative electrode potential value is equal to 0, then that shows the hydrogen curve. Okay, so that's why the copper cannot reduce this hydrogen. Okay, hydrogen can reduce the copper because it has a higher value than this. Okay, this is the chemical reactivity. Okay, so next thing is, students, next property is magnetic property. Okay, you know in the solid state chapter I already explained what are different types of magnetic properties or magnetic substances. And paramagnetic is there, diamagnetic is there, and ferromagnetic is there. Okay, so in these D block elements we are going to explain only para and diamagnetic. Some show ferromagnetic, but that is nothing but equal to a paramagnetic only. Okay, we'll study with the para and diamagnetic substances. Para and diamagnetic. Okay, so here how we can came to know which one is paramagnetic, which one is diamagnetic, means that is based on their electronic configuration. How we can calculate, students? This is another property, that is sixth property is magnetic property. Okay, so here you know mu is equal to square root of n into n plus 2. So this is the formula to calculate what? Magnetic moment. So mu is equal to what? It is magnetic moment. Okay, n is number of unpaired electron. Okay, so this is represented by our unit of Bohr magnetic is, that is Bohr magneton. Okay, this is the formula to calculate the magnetic moment of the electrons which are present in the D Okay, by taking the 3D series, I will explain how we have to calculate magnetic moment, how the number of electrons based on decides the para and diamagnetic character in the next class. Thank you.